Hello, my name is Marco Riani.
And my name is Anthony Atkinson.
The purpose of this video is to talk about robust Bayesian regression.
For most of this book, we treat each data analysis problem as something separate from any other experience that has been had. But it is certainly true that in many cases you do bring to your data analysis some knowledge of reasonable sizes for parameter estimates or knowledge from earlier studies. The material in this section covers such Bayesian approaches. We continue to consider normal theory linear regression. If we have a prior distribution, we combine it with the log likelihood to get a posterior distribution. A conjugate distribution for a particular problem is one in which the prior distribution combined with the log likelihood leads to the same distribution again, but with different parameter values. For the normal distribution, the conjugate distribution is called a normal inverse gamma conjugate family of prior distributions. The inverse gamma refers to the distribution of 1 over sigma squared, which is called tau, sigma squared itself, or the estimate thereof, having a chi-squared distribution. Fortunately, for this conjugate family of prior distributions, it is possible to obtain the parameters of a prior distribution through the use of a distribution of fictitious observations. We summarize our prior expectations in a distribution, and then we can estimate the parameters of the prior distribution. We start with sigma squared. Let the estimate of sigma squared from n0 fictitious observations be S0 squared on nu0 minus n0 minus p degrees of freedom. Then in the conjugate prior, there are two parameters which describe the distribution of the estimate of sigma squared. They are A0, which is nu0 over 2, which is equal to the number of prior observations n0 minus p divided by 2, and B0, which is nu0 S0 squared over 2, which is the residual sum of squares of the fictitious observations. These are then the parameters that we need in the inverse gamma part of the conjugate distribution. Prior information for the linear model is given as the scaled information matrix R, which is x0 transpose x0, and the prior mean beta hat 0, which is r to the minus 1 x0 transpose y0, where y0 are the fictitious observations and x0 is the extended design matrix for the fictitious observations. Then S0, the residual sum of squares from this fictitious observation, is the total sum of fictitious sums of squares y0t y0 minus beta 0 hat transposed r beta hat 0. Thus, given n0 prior observations, the parameters for the normal inverse gamma prior may readily be calculated. Given the prior distribution of the parameters and given some data, y and x, we can then find the posterior distribution of the parameters. The posterior distribution of beta, conditional on the value of tau, is a normal distribution with beta 1 hat as its mean, an information matrix which combines R and the observed x transposed x. You can see that information is, we take the inverse of that information matrix. We can then rewrite this in a different form in the third line of 8.5. We get a weighted expression which contains the matrix A, which is R plus x transpose x to the minus 1 x transposed x. It shows that the posterior estimate, beta 1 hat, is a matrix weighted average of the prior mean beta 0, and the classical least squares estimate beta hat with weights 1 minus a and a. If prior information is strong, the elements of R will be large and A will be small, so that the posterior mean gives most of the weight to the prior mean. In the classical approach, these weights are fixed, while with the forward search, and this is very important, while with the forward search, as the subset size grows, the weight assigned to A increases with M. We can dynamically see how the estimate changes as the effect of the prior decreases. We have so far given the posterior distribution of beta. The posterior distribution of tau has parameters A1, which is A plus n over 2, that is n0 plus n minus p over 2. n0 plus n being the total sample size for the fictitious observations and the true observation.
So the posterior distribution for sigma square is an inverse gamma with the new parameters A1 and B1. Remember that the prior parameters were A0 and B0, and the posterior distribution of beta is multivariate T with the value of sigma square, which is the inverse of the posterior mean estimate of tau, and as a variance covariance matrix which depends both on x prime x and on r. R is our x prime not x prime not.
So far, up to equation 8.9, we have been considering all the observations. However, there is one complication in this procedure when we come to consider it for the forward search. The n0 fictitious observations are treated as a sample with population variance sigma squared. However, the m observations from actual data come from a truncated distribution of m out of n observations.
Because in the search our m observations are those which fit best the model.
Asymptotically, these observations have a variance which is given by sigma squared t m sigma squared,
where sigma square capital T is the expression of the variance of the truncated normal distribution. If you now have the book in front of you, please go to equation 3.49.
So, an adjustment must be made before the two samples are combined. This becomes a problem in weighted least squares.
Therefore, here we are combining a normal sample with a truncated sample. The normal sample comes from the fictitious observations, the prior observations. The truncated sample comes from the M observations during the forward search. Therefore, in order to have an unbiased estimate of sigma square, we have to take into account that the variance which is estimated using the M central observation is a biased estimate of sigma square, because our M observations are the best out of M, and therefore have a variance which is equal to the variance of the truncated normal distribution, where the truncation proportion is M subset size divided by N sample size. All the mathematical details are given in equations from 8.11 to 8.15. The outlier detection procedure in the Bayesian forward search is based on the minimum deletion residual, and the form for the minimum deletion residual keep into account that we have these two samples.
As a result of monitoring, we can see whether the prior values of the parameter agree with those that are provided by the sample. In particular, we can plot a horizontal line for the prior value of the parameter estimates, and if there is a divergence between the prior value and what the message is that is coming from the data, then the estimate of beta hat will move away from the prior distribution and be far from it.
Now we see these things online.
We start with the analysis of some data on the price of houses in Windsor, a city in Canada. The data are the sales prices of 546 houses. The full set of data, we give the reference to where it can be found, gives information on 12 explanatory variables. A Bayesian analysis of these data was given by Coop, who used 4 variables. We follow him in this. The variables, you can see them there, all have to do with things to do very much with the description of the house, rather than, for example, with its location or the kind of area that it's in, or its age for that matter. In Coop's Bayesian analysis, he derived, perhaps by the pricking of his thumbs, some prior values. In table 8.1, we give the prior values given by Coop and also a partial least squares analysis that we have done. The second column of the table gives his prior values for the parameters of the linear model, and in the last row the prior value of tau. The third column gives his estimates of the diagonal elements of the prior information matrix. The last column gives it the corresponding elements from a least squares analysis. What we notice in particular is that there is not a strong agreement in the estimates between the fourth and second columns, but that the last entry in the third column shows that n0 was taken equal to 6, which is a very small number given a model with 5 linear parameters and needing to estimate sigma squared. So we can expect that the effect of the prior information may be rather slight.
Okay, so now we load the data, and it is not given in the book, but we start with the y-x plot.
Okay. We're now showing a y-x plot of these data. Y is the sales price of the house in Canadian dollars. X1 is the plot size of the house in square feet. X2 is the number of bedrooms. X3 is the number of bathrooms, which for those of us living in small European accommodation seems quite amazing. And X4 is the number of stories in the house.
There is a clear increasing relationship between X1, the plot size of the house, with the price. Then it also seems that there is a positive relationship also with the other 3 explanatory variables, although it is not very clear how strong it is.
Figure 8.1 shows the forward plot of minimum deletion residuals, a well-behaved curve for the greater part of the data, with the signal for outliers first occurring at m dagger is for 511. The usual superimposition of envelopes leads to the identification of 18 outliers, so that the first outlier is at m is equal to 529.
The outliers which are found are shown in figure 8.4.
Rather disconcertingly, almost all these outliers occur for large values of y. We next turn to figure 8.2, which shows the effect of prior information as opposed to sample information on the parameter estimates. In this figure, there are 5 panels for the constant and the 4 regression parameters, and there is one panel for the estimate of sigma squared. In each panel, there is a continuous horizontal line, which is the value of the parameter given by the prior, and around that we have 2 sets of dashed lines, blue and then red, which are the 95% and 99% higher posterior density regions for the parameter estimates for the linear model. Although there are a large number of observations, 546, we're interested in what happens fairly near the beginning of the search. So we start from m is equal to 20.
We finish with m equal to 125.
We see that all the figures are really very similar in shape. At around m is equal to 40, information from the data starts to outweigh the information from the prior, and the bands of the HPDs become narrower. For the 5 parameters of the linear model, the difference between the continuous red line, which is the value given by the prior, and the parameter estimate, which is given by the black continuous line, is not too great. One thing to remember when looking at these plots is that the black continuous line was plotted first and the red continuous line was plotted afterwards. So, in fact, if you look at the panel for beta 1 hat, you can see that initially there is complete agreement between the two, although later on the two estimates separate. The estimate for beta 0 hat is always below the prior estimate, and so forth. The really outstanding divergence between prior estimates and sample estimate is in panel 6 for the estimate of sigma squared. The continuous red line is always outside all the HBD trajectories that we have plotted. We now turn to the second half of the search in figure 8.3, which is similar to figure 8.2 in what we are plotting, although not in content. This is looking at the second half of the search, and we see that the envelopes for some cases move up and down, but on the whole, generally speaking, the envelopes no longer lie at all around the prior value, this horizontal red line. This is especially true for beta 1 hat, and for the estimate of sigma squared it's even more so. And for, I suppose, the next one working away is beta 2 hat. What we would like really to stress about is not so much about these particular parameter estimates as to what an informative tool to monitoring plots from the forward search are.
In this plot, we also have a red vertical line. The red vertical line indicates the subset size for which we start finding the outliers. And you can see the effect of the outliers, for example, on the estimate of beta 2. That is, the entrance of the outlying observation cause an increase in the value of beta 2. The opposite is true for the estimate of the intercept, and generally the outliers correspond to an increase in the estimate of sigma square. Now we end this analysis with the frequentist analysis, that is the analysis that does not use any prior information.
We now repeat figure 8.3, which was for an analysis including prior information. We now compare that with the least squares analysis over the second half of the search, that is from m is equal to 250. We notice that the final part of the search from least squares is exactly the same as that from using this very weak prior information. However, in considering any of these plots, we should remember that the forward search does start from a random point, although it's carefully selected, and it may be that for small sample sizes, the effects differ from one search to another.
Of course, one could increase the number of initial subsets to compute the initial estimator, but what is important is that the last third of the search is never affected by the initial subset with which we start the search. Also here we have the vertical line. The vertical line refers to the point in which the outliers start to enter, and also in this case you can see the effect mainly on beta 2. The outliers are increasing the estimate of beta 2. The conclusion from this example is that the monitoring of the estimates and or other quantities in the Bayesian for research not only enables us to understand what is the effect that each unit exerts on your model, but as an additional benefit enables you to understand how much is your prior in agreement with the sample information. The second example that we consider refers to the imports of lobsters into the European Union. We have data referred to 3 years in the period 2002 to 2004. In the first year, the number of observations is 165. We load this data and we show the plot referred to year 2002. On the x-axis you have the quantity in tons and you have the value in euros multiplied by 1000. You can see that there is a very strong relationship between y and x, and you also see some observations which seem to depart from this main regression line. Finally, notice the initial part that is made up of many observations. Okay, if you look carefully at the initial part, you can see some heteroskedasticity. Please refer to the video on heteroskedasticity that has been published.
We mentioned heteroskedasticity of these data, but it is perhaps of a rather different form from that we have seen before. It seems to come from the superimposition of several regression lines. There's quite a nice little line down at the bottom for very small quantities, which appears to be quite different from the line for the majority of the data. This kind of structure will be something that we are particularly interested in, and we will find that analysis over several years draws it out very nicely. In our first example, we took a prior which came from fictitious observations, and we used that in the analysis of our data and saw how it did or did not agree with the data. Here, in the second example, we have data over several years. We use least squares to fit the data coming from the first year. We use the parameter estimates from that first year as prior information to analyze the data from the second year.
So for the first year, we do a frequentist for search, that is a search that does not use prior information. Then we plot the units that have been declared as outliers. Note that here we have three symbols. Both the red and the purple symbols referred to units detected as outliers. We distinguish between red and purple depending on their deviation from the fitted line. In other words, given that here there is a very strong relationship between y and x, the estimate of sigma square is very, very small, and the estimate of r square, vice versa, is very, very large. When the estimate of sigma square is very, very small, it is enough a very small deviation from the fitted line to declare a unit as outlier. On the other hand, here, for economic purposes, we want to concentrate on the units which have a deviation from the fitted line, which is based not only on the p-value, but is based on a physical interpretation. So here we imposed that the observation that have a residual in absolute values smaller than a certain threshold cannot be declared as outliers. So here we have three symbols. We have the blue plus, which are the units that have not been declared as outliers. We have the purple crosses, that are the units that have been declared as outliers but have a deviation from the fitted regression line smaller than a certain threshold. And we have the red unfilled circles, which are the units that have been declared as outliers and that have a deviation from the fitted regression line, which in absolute terms is greater than a certain threshold. For example, look at this purple point. This is very close to a normal unit, and from an economic point of view, it doesn't make any sense to investigate this observation. On the other hand, these are the observations that you wish to investigate. I mean, those which have a declared price. Remember that for international trade data, the slope is the estimate of price. Therefore, the observations that are below the regression line are the transactions that are associated with declared price significantly smaller than that of the majority of the data. Now we move to the second year. In the second year, we have a prior that is made up of the units that or had not been declared as outliers in the first year, or had a deviation smaller than a certain threshold. We do outlier detection, and now we create figure 8.10.
Here is a plot just of the 2003 data, since we have used the 2002 data just to generate our prior values. We see here again that we have an appreciable number of observations that are not reckoned to be outliers. We also have some purple crosses, which are declared as outliers but are not thought to be of economic importance. And then we have red circles, which we do believe to be outliers and may be economically important.
For now, we have the data from 2002, where we had good and intermediate observations, and same thing for 2003. In 2003 also we have the blue and the purple units. So using the blue and purple units both from 2002 and 2003, we form a prior, a combined prior. We do outlier detection on the third year, and we now show the output for the third year. And also for the third year, we have units coming from three colors. We have the good units, then the purple crosses, the so-called intermediate units, and we have the unfilled red, that is the observations that have been declared as outliers in the third year using a prior based on good intermediate units for the first 2 years, and these unfilled red are the units declared as outliers that have a deviation from the fitted regression line which is greater than a certain threshold.
This threshold came from talks with experts in financial and legal matters.
We want now to point out that if you receive data every year, it is important not to start every new year from scratch. Therefore, the Joint Research Centre of the European Commission takes into account and forms a prior information using the units that had not been detected as outliers in the previous years. This enables to have strong prior information. Therefore, slight deviations from the fitted regression line are immediately detected as outliers. In the simulation studies, not given in this book, we have shown that if you have a correct prior, your average power is much greater than the one which does not use prior information. Let us come to the conclusion for this Bayesian analysis.
The structure of figure 811 is, in a way, similar to the scatter plots from the two earlier years. However, the line of contaminated or outlying observations, the red circles, does seem to stand out more clearly. One might ask, what is the point of using this prior information? Surely you could just take all 3 years' data and analyze it all together. You will have a larger sample, so you will have more power than if you just look at the 3rd year on its own. This is true, but much more information can be obtained. Much more powerful results are found by using the prior information from the previous years once we have used the forward search to clean it of outlying or semi-outlying observations. That will increase the estimate of variance, make the parameter estimates less precise, and so make outlier detection much less sharp. Greater power is obtained, and we've shown this by simulation studies, by using this sequential Bayesian procedure.
Thank you for watching, and see you to the next video. Ciao.
Ciao, arrivederci.